Hi, I'm Philip, and in this video I will show you my reverse engineering process of a Tupperware Grater. So basically what issue I had with my grater was that there is like this central piece, or plastic piece, that holds the grate, or the grating kit. And on the end there is like this custom thread that it engages with the cranking handle. Problem is it's like very flimsy, thin extruded plastic or die-cast plastic with, I think it's like 2 millimeter thick, and so currently it simply doesn't hold and it broke. And I could buy replacement parts for this unit, that's true, but the problem is the replacement parts will have the exact same issue, and especially when grinding harder nuts, it will arise again. So what you also can see that this grater has like a notch cut out that engages with the plastic part and holds it in the right direction, and this one is also not working as it should on the original plastic part. So first thing, of course, was 3D scanning, and then comes the design. So for scanning, I simply placed the original defect part on a base of markers, so marker cards and marker geometries. You can also see a bit here in the inside that I used super glue to glue the broken thread again. So I have the original model because it was a bit warped and deformed due to breaking. So I just glued it together to get the original shape. I scanned it from two sides with the Einscan Rigil, so from the top and from the bottom, and then just aligned them. And the final scan result looked quite nice. So it wasn't done with any scan spray. It may have been beneficial, but the outcome was simply good enough for me to use. So no need to spend additional time on scan spray and clean up. And then it goes to reverse engineering. Before we start reverse engineering journey, I will show you the final part, how it will look in the end. You can see here, this is like the first test print with a bit wet PETG, so don't mind the surface imperfections. I reprinted it from foodsafe plastic again, so this was the first test. But the final part is thicker. The top thread section is solid, so it won't break again, or not at least at this point. And as you can see, it meshes nicely with the handle, and also the notch here engages much better. So we can start with reverse engineering. And before we start, I again want to give you a quick overview of the steps we take, so you can like use them as a guide or keep them in mind. So first thing, of course, Quicksurface. So I completely decided in Quicksurface Pro is import of the scan and alignment. So alignment is a quite important step to start with, because this dictates, for example, rotation. Because it's a rotational symmetric part, I need quite a good alignment to get like a proper fit later. Then the next step is building the base of bodies. So this is mainly if we think of the grater like such a part. So you can see it with the thread here on the top. The base body is, this is a base body, this is a base body, this is a base body, and then the thread is like a own section that's a bit more complex. And for all these, you can simply use sketches and extrude or rotate. Extrude or rotate. Then the third step is creating the cutout. So cutout for grater. So this takes the original model, and then I add like this. The cutouts are added, and these are also again as like a rotation of sketches. And for this to fit them nicely on the original body, I use analysis tooling. Yes, I'm sorry, analysis. So to compare the mesh to the cat model, or to the cat part. So this is especially important for filleting to get a nice fit. And then the fourth and final step will be creating the thread, or the thread section. And for this, I just use, I first create a helix following the original thread on thread, like this. Then we create a thread profile. And then we can loft the profile on helix. So this is already all the important parts for the modeling. So these are the 4 base steps, and as always, there is like filleting and a bit of forth and back with analysis tooling to get a nice fit. So some of these steps would also be possible, could be possible in traditional CAD tooling, but especially this section, analysis and fitment of sketches, this is where like proper RE software is shining. For me, it's Quicksurface. So now we got a rough concept of all the included steps in the design process, and we can go into Quicksurface. So this is the latest Pro version, so it's the 2026 version. All the steps I'm showing here should also work in last year's version, so 2025, because there's not too much complex filleting involved, or the CAD modeling is also a bit more basic. So the first thing we will be doing is aligning the mesh. You can see, okay, currently it is already aligned, but I nevertheless will show you how it is aligned. So we start with the prepare scan tooling. So this is most of the time my first step. With the prepare scan, you have the option to either delete like smaller users meshes you don't need, already edit the scan and delete any unneeded parts, or fill holes as needed. For example, here I could fill this hole, but since we're doing like reverse engineering, the goal is to not like create any artificial data that we don't need. So I won't be editing it too much at this point. The one major thing that I may be doing, or do most of the time, is reducing the triangle count. So you can see here, currently we have roughly 800,000 triangles. Originally, I think it were like 2 to 3 million. So I used a bit too low resolution actually. But this just makes it a bit easier. So I have quite a powerful workstation. So it's you can have a look here in my like task manager. You can see with the hardware. I have a 16-core processor, 128 gigabytes of RAM, and a 5070 Ti. So I can handle up to roughly, I would say, 20 million triangles at a time to get like a smooth processing experience. But it's not needed. And what's also quite good in Quicksurface, so if you reduce the polygon count, you can see here, per default it is set to 50% reduction rate. So let's preview it and now go into the deviation analysis. So currently we everything that's within 1/20th of a millimeter, so 0.05 millimeters, is still is of the new mesh, or the reduced mesh to original mesh, is still within. We see 100%. Now we can even reduce it further. Let's try 10%, so 80,000 triangles, and it's still within the 0.05 millimeter tolerance. If you go down to 0.01, we can see now we start to get some outliers. So you can really reduce down the data by much more than you may think is possible. So first thing for the scan is now we imported it, and now we will look at the alignment step. So for alignment, I first created a cone on the outside of the body or of the cylinder. This will define my z-axis. So I get like the option to perform proper rotational modeling. And then I still need 2 additional planes to define the other 2 axes. So the first plane will be to define the XY plane. So this is just here on the interface. This is the interface to original grind, and it's perfectly flat or relatively flat. And the next one is for the rotation around the z-axis. And for this one, I just used a symmetry plane. So I fit a symmetric plane. All of the 3 geometries were created as part of the prepare scan. And then I can orient it to the coordinate system. I start with the cylinder to get like the z-axis defined. Then I use the base plane and this as the last plane to lock in the rotation. Now, as we have aligned the model, we can already start with extracting our primitive bodies. So the first one will be this lip. So I just, the down lip. So I just create a 2D sketch. And as you can see, I even make my part a bit thicker than the original design. So reverse engineering for me always means also to some degree trying to improve the modeling or the model and not just simply replicate it unless it is needed or wanted. And what you also can see here, that it is, or the original part isn't a perfect circle, but I still constrained the new circle to the origin, just to have proper rotational symmetric part in the end. I do the same for the upper part, also a bit thicker, just to get some extra material in there, because the printing direction or printing setup will be like this. And I want to have like the proper layer adhesion in these thinner bridges. And for this, I just use a bit more material because the original design was quite flimsy. Now we can already extrude them. And for this, I just use the snapping tool. And while snapping, you can always analyze. So here you can see to 0.1 millimeters, and it's quite a nice fit. Of course, it's like a plastic or extruded plastic. The tolerance won't be this good. And then the third sketch is already a rotational sketch for the core body. When creating a rotational sketch, you can see here, I can revolve it. You can freely move it around until you find a spot where you like have the best intersection or the intersection you want for your design. So I did it here, so there is no hindering geometry, and it's like the thickest part of these bridges. Then I can already revolve it or revolve the surface. So I have one body and start with a bit of like, smaller cleaner tasks. So here I chamfered the inside to get like a nice outlet because I wanted the outer lip to be roughly similar to the original design. So you can see here 0.1 millimeter tolerance, and like the outlet where the grindings will fall out or drop out, they are within 0.1 millimeters of tolerance. So now we can, if you have a look, we have, first step is completed. We also completed the second step, and now we will look at creating the cutout for the grater. For this, I will first create, I still missed another cutout. So this is the cutout here for the, where the connecting piece of the grater grid will go. For this, I first create an additional small sketch and extrude it to get the notch. And then I will define a few planes. So if you hide the body, define a few planes to basically constrain all of the sides of this cutout. Then I can trim the planes together to get a body and create a second trim operation with additional plane here in the bottom to create a cutout. And then I can just use the trim tool. So you can see I use the trim tool to create a new body. If I show the remove surface, you see that I remove the cutout. Why did I use multiple separate trim operations if I could have also used them in one step? So performed all of this trim in one step. The reason is that While trimming, each intersection of a plane to another plane or body creates new separate parts that you have like to deal with. You have to like select, do you want to keep them or do you want to remove them? There is theoretically also an automatic trim tooling, but for more complex shapes, the outcome isn't the best. So it works best if I have quite nicely. So basically imagine you have a cube and you define 6 planes on the outside of the cube. So you have a nicely defined body in the inside, and then the automatic trimming works excellently. But for the more complex ones, and especially for like open shapes, manual trimming is still preferable. And with this, I just want to reduce like the complexness of the single steps. I initially also thought about creating a rotated sketch here and extruding it. Problem is that these sides are a bit chamfered to the top, so the slot is getting wider, and just extracting the planes or fitting planes made it possible quite easily. For plane fitting, what's important that, for example, if we now extract a primitive and fit a plane here, and like this, you want to have a close look at the constraining, or how it is constrained. So for example, parallel, we will say it is perpendicular to the YC plane. So this is what we want, because now the plane is symmetric to the YC plane. If I would say it's perpendicular to the XY plane, you can see it doesn't fit at all, and without any constraining, it won't be fully symmetric. It will still work as a model, or still work, but the quality of the final design will be a bit inferior, I would say. And it may be a bit harder if you later take the reverse engineered step model and want to continue in traditional CAD software. It will make things just a bit harder for yourself. So now we go to the cutout. For the cutout, I just created a sketch. And again, I rotated the sketch, and as you can see, it's in the apex, the widest part of the cutout. Then I can rotate it, while again using fitting or snapping to the sides. And as you can see, I already see the tolerance. So it's roughly within 0.1 millimeters. And so that's quite nice. And what I now can do is I can first use the fitting tool, or use the analysis function to first chamfer the model, and then fillet it to fit roughly nicely into the cutout. I am aware that it isn't a perfect fit. So now if we compare, you can see there's still a few rough spots. But due to the fact that I'm like, this isn't a relevant interface part. So this is only a cutout where the grindings will fall through. It's completely irrelevant to get a perfect fit. It would just increase the modeling time exponentially. And like, why should I do it? Now what we already can do is use the circular pattern tool to create a pattern of these cutouts, and in the next step cut them from the original body. And we can see finally our design is taking shape to be quite closely to the original model. Going back to our to-dos, so we can see, okay, our cutout is nearly finished, and now we can do a bit more of filleting to clean it up a bit to the design. So this only means we'll apply internal, external fillets, and the next thing already will be designing the thread, or the top thread section. For this, I will first create a sketch to get basically the core body. So the internal face of the thread, so you can see here, where it's like a cylinder shape, and the thread is applied on top of the cylinder. For this, I just created a sketch, and this will later be extruded to create the solid centerpiece. The next thing is creating a helix. Creating helixes in Quicksurface is actually quite easy. So if you have a look, surface, then we can select the helix tool. I will pick the Z axis as my base for the helix. And now I can already, where we go, helix, start point. I can pick it here. now I can pick the endpoint here, and I can auto adjust, I can measure the pitch. If we have a look from the side, the pitch will be from here to here. And the helix is already taking shape. I can now auto adjust it, and as you can see, it is fitting quite nicely. And what you now again can do, you can extend the start and the finish in a natural style. That's the one I like to use. And we already have a finished helix that we later can use for lofting. So the you also can create a taper, since this is like a molded part. It will have a taper. In reality, you won't need it. It's more like a limitation of the original manufacturing method. So let's delete it and show our helix again. Then what we'll do is a few more filleting. I noticed in between I wanted to continue, so I could have cleaned it up a bit more and sorted the steps, but it's fine for me. So now I will create the thread profile again as a rotated sketch. Basis for this profile is the original sketch I did for the central cylinder, and I had a bit of attention that it is inside this profile, so it will nicely combine later. And I also can use the sweep tool. Sorry, I initially told you that I will use the loft tool. It's a sweep tool. Loft would be between sketches. Sweep is basically sketch along the path. So back to design. So I can use the sweep tool, and as you see, let's hide sketches. We have a quite nice base shape for the thread count. And now if we compare it, let's say to 0.2 millimeter, you can see that it's fitting quite nice. There are a few imperfections, but the final design worked. So with these plastic die cast designs, there's often quite a lot of play in the cylinder. And this is also a bit of the reason why the original part broke, because it was a bit loose fit. So now I can again extrude the central body, and if we hide the other body, what my next step will now be is, you can see the threads are a bit like overlapping from the top and from the bottom. So I will simply define the top plane and the bottom plane again, as you can see here, and I can use the trim tool to clean it up a bit. I just remove the overhanging area of the threads. And the last step to complete this design is just combining the two bodies, and we are finished now. So I hope this gave you a bit of an idea or a better impression how to design a Quicksurface. Now the model has been in use for I think it's like 3 months, so I forgot to record a video for some time, and it still holds up, and it's holding up better than the original part. So yeah, I hope you enjoyed, and be back for additional tutorials and 3D scanner related topics.